Welcome to today's video. So today's video is a part 2 of our rate of reactions series. But for today's question, we're going to be taking a look at the 2023 June exam question paper. So let's see what they had to write. So consider the following decomposition reaction that takes place in a sealed 2 decimeter cube container. So we've got the chemical equation written for us there, and we can see that it's balanced. And then we're further on told that the graph below shows how the concentration of nitrogen N2O5 gas and NO2 gas change with time. Okay, beautiful. So just by looking at the graph, I can see that I've got one graph A, I'm going to put in blue, that's increasing as time increases, and then graph B that's decreasing as time decreases. So already I can tell you that graph A would represent your product, and then graph B would represent your reactant, because in any chemical reaction, the reactants are being used up and the products are being formed. Okay. All right. 5.1 asks us to refer to the graph above and give a reason why curve A represents the change in the concentration of NO2, right? So graph A, we could see it starts at 0 and then increases with time. And that's our reason, okay? That's the reason why it represents NO2, because NO2 is a product. It starts at 0 initially, and that's at time 0. We've got no products. And then over time, it slowly starts to increase, and which is exactly what is happening here, right? So we could say the reason is because curve A starts at 0. Let's look at 5.2. So in 5.2, we're asked to consider the statement below. We're told that the rate of decomposition of N2O5 is half the rate of formation of NO2. So they've got a 1:2 relationship. Okay, is this true or false? And give a reason for your answer. All right, so let's put this to the test. Okay, so I'm just going to choose a random time. Let's say after 100 seconds, and let's see. Okay, so after 100 seconds, remember graph A represents the NO2. So graph A, remember this is NO2 and this is N2O5. So for graph A, after 100 seconds, I've got around about 60 moles per decimeter cubed of the NO2, okay? And after 100 seconds, I'm down to about 170 moles per decimeter cubed of N2O5. So there's about a decrease of 30, okay, 30 moles per decimeter cubed. So we could see that after 100 seconds, 60 moles per decimeter cubed of NO2 is formed, and at the same time 30 moles of N2O5 is lost. Okay, so this statement is therefore true. There is a 1:2 relationship. Okay, so to answer that question, we just simply say yes, it is true. And you could say that at 100 seconds we had about 60 moles per decimeter cubed of NO2, and we lost about 30 moles per decimeter cubed of N2O5. That's simple. So let's take a look at question 5.3. So 5.3 asks us to calculate the mass of the nitrogen gas present in the container at 400 seconds. Okay, so let's 5.3.1. So at 400 seconds, if you take a look at 400 seconds right over there, we have about 200 moles per decimeter cubed. So the way this graph is drawn is that we have concentration, and in bracket we've got times 10 to the minus 4. So what does that mean? That means all of these values that we have here need to be multiplied by times 10 to the minus 4. So it's not just 200 moles per decimeter cubed, it's 200 times 10 to the minus 4 moles per decimeter cubed. Okay, so at 400 seconds, we've got the concentration of NO2 to be 200 times 10 to the minus 4 moles per decimeter cube. Okay, so if we do the math there, so 200 multiplied by times 10 to the minus 4 should give us a concentration of 0.02 moles per decimeter cube. So that's the concentration, but we're asked to calculate the mass of the nitrogen gas that was formed. Okay, so how do we do that? So first we need to get the number of moles. So number of moles is equal to concentration times the volume, so CV. Alright, so for concentration we have 0.02, and then the volume, it's given to us as 2 decimeter cubed, so we've got multiplied by 2 there. If you do that math, you should get 0.04 moles. Okay, so that's the number of moles of nitrogen gas. All right, so if you want to have the number of moles and you want to get the mass is equal to the number of moles multiplied by the molar volume. Right, so molar volume of NO2, we use the periodic table to get the molar volume. So we've got nitrogen, 1 nitrogen molecule, and 2 oxygen molecules. Okay, so you've got 14, that's the molar volume of nitrogen, plus 2 oxygen molecules, and oxygen has the molar volume of 16. So if you do the math, that means the molar volume here is 46 grams per mole. All right, so now we can substitute. So I know the number of moles is 0.04 and the molar volume is 46. So 0.04 times 46, that should give you the mass of 1.84 grams. Okay, so that's the mass. I should write it in small letters. That's the mass of the nitrogen gas that is present at 400 seconds. NO2 gas, rather. All right. 5.3.2 asks us to calculate the average rate of production, okay, of O2 gas in mole per decimeter per second. So this part is concentration, and that part is per second, okay, in 700 seconds. So this is that to calculate the average rate of production of the O2 gas. So in 700 seconds, we don't know, right? We don't have a graph for the oxygen gas, but we do have a graph for the NO2, and we do have the graph for the N2O2, right? So we're going to choose one of those. So I'm going to go with the graph for NO2, and I'm going to calculate the rate at which NO2 is formed, okay? And then I'm going to have that at the back of my mind. So once I've got the rate of NO2 is formed, how do I now get the rate of oxygen gas that is also formed? So I can see that from this balanced equation, there is a 4:1 ratio, okay? So we're actually going to use that ratio to figure out what is the rate of the oxygen gas. So first we're going to get the rate of reaction for NO2, and then we're going to use the stoichiometric ratio to get the rate of the O2 gas. So let's see how that is in practice. So if I go to 700 seconds, at 700 seconds, I go and trace it back there. How much is that? So maybe let's use a little bit of a thinner line. Right about 700 seconds, the concentration hits there. So this will be 260, this will be 270, this will be 280. So we've got 280. Remember, it is times 10 to the minus 4, okay, moles per decimeter cube. So that's the concentration of the nitrogen gas that is formed in 700 seconds. Okay, so initially we had 0, and after 700 seconds, we had 280 times 10 to the minus 4. Okay, so let's use that. So 5.3.2, I've got the average rate. Remember, this is of NO2. Okay, so equals to the change in the concentration of NO2 divided by the change in time. Okay, so that means we've got concentration of NO2 final minus the concentration of NO2 initial divided by time final minus time initial. All right, so the concentration of NO2, that's how much of NO2 that was formed at 700 seconds, and we found that to be 280. And then initially is 0, because at time 0 we had no product. Okay, so we had no concentration whatsoever of NO2. So this is 280 minus 0. The time final is 700 seconds minus 0. Okay, because at time 0 is 0. Okay, all right, so we put all of that in our calculator. That tells us that the rate of production of the NO2 gas is 0.4 moles per decimeter per second. Okay, and that is the average rate of the NO2. But that's not what the question asks. The question is asking for the average rate of the oxygen gas. So how do we get that? So NO2 to oxygen, okay? Right, so if you go back to our chemical equation here, like I said earlier, there's a 4:1 relationship. So 4:1, right? So I already know my rate for my NO2 is 0.4, and what I'm looking for, I'm going to label it as X, is my rate for my oxygen gas. So now when I get here, what do I do? So just simply cross multiply and try to solve for X. So when I cross multiply there, I've got 4X is equal to 0.4. Therefore, X is equal to 0.4 over 4. And that should give you the answer of 0.1 moles per decimeter cube per second. And remember, now this is the rate at which oxygen gas is produced. Okay, 0.1 moles per decimeter cube per second. So just to recap what exactly we did here. So what we did was, the question asked us to find the average rate of the oxygen gas at 700 seconds, rate of production of oxygen gas in 700 seconds. But we didn't have a graph for the oxygen gas. Okay, what we did have a graph for was the NO2 and the N2O5. Okay, so we chose to use the NO2 and found the average rate of NO2, and then use the stoichiometric ratio right, to find the average rate of O2. Okay, and you're allowed to do that. Okay, so that's a neat trick that you can always have at the back of your mind. Wonderful. Let's look at the next question. So the next question is the Maxwell-Boltzmann distribution curve for N2O5 gas initially present in the container is shown below. So we've got number of particles versus kinetic energy. So that's the graph. So that's initial graph of P. And then we're told that the initial concentration of NO2 gas is now increased. Okay, so what is increased? Concentration. And we're asked to redraw the distribution curve above in the answer book, label as P. Okay, on the same set of axes, sketch the curve that will attain at the higher concentration and label that as Q. Okay, so we already have the P graph drawn for us, and the question is basically asking us to draw what would the Q graph look like now that I've increased the concentration. Okay, so according to Maxwell-Boltzmann, because you increase the concentration, your graph is going to look something like that. And that should be Q, because the number of particles has gone higher. All right. So a higher graph like this, and that's how you're going to get your 2 marks. Beautiful. 5.4.2 is asking, will the rate of decomposition of N2O5 at a higher concentration be higher than, lower than, equal to the original rate of decomposition? Explain your answer using the collision theory. Okay, so this is a beautiful answer. So to do this, we're going to go back and write this in bullet form again. So it's question 5.4.2. So simply we say when concentration, okay, and in our case we've got N2O5 is increased, okay, so you increase the concentration, you've got more particles, right? So because you've got more particles, you've got more collisions, okay, or you could say particles, okay, now collide more frequently. That word frequently just means more often, okay? And because you've got more collisions, therefore you will have more effective collisions per unit time, and therefore the rate of the reaction will be faster. Okay, so anything that you change in the system that allows for more effective collisions per unit time will always increase the rate of reaction. So first part of that answer should be higher than. Okay, so we're actually supposed to say higher than. Okay, and then give this explanation. Okay. So the rate will definitely be higher because concentration was increased. Because we should know that concentration is directly proportional to the rate of a reaction. Okay, so what does that mean? That means when the concentration increases, the rate also increases. When the concentration decreases, the rate of the reaction will also decrease. Wonderful. And that's our answer.